Okay. All right. Hello, guys. Welcome to the live stream. Today we'll be going over a problem that's part of our second mock competition. So that is the name of the mock competition. If you guys go to VJudge and you search it up, you should be able to see it and you should be able to participate. Let's just look at the overview. So we have 5 problems. 3 of them are about the greatest common divisor. That's kind of combinatorics, how Gary went over last class in the beginning. Some of them are easy. For example, the E. Problem E is a little bit simple, just to give you guys some confidence. But A and B is a little bit more challenging, might require you to think about it a little bit more. But what we're going to be doing today is actually problem C, which is PizzaParty. And this is also a problem that Gary went over. Let me just put it right here so you guys can see it. Yeah. And now I got requested to read it out loud, so I guess I'll do that. You're a co-organizer at a computer science conference, and you go around tables asking people what type of topping they want on their pizza. There's 2 types of things that people can say. They can either tell you a implicative preference. Is that the first one? No, the first one is an absolute preference, where they tell you that they have to have pepperoni or they have to have sausage or whatever other topping. The other type of statement is implicative, where it's conditional. It could be, if there's pepperoni and there's sausage, then I want cheese. Or it could also be, if there's pepperoni or if there's peppers, then I want mushrooms. So those are the 2 main statements. Huh? You don't think I read it right? Okay. So those are the 2 types of statements, as you can see right here. The first one, sample 1, peppers, that's an absolute statement. It's telling you that they have to have peppers, so you for sure are going to be having that topping. The second one is an implicative. It's implicative with the and. So they need both spinach and olives. If they have both of those, then they would want tomatoes. And like I said, there's also ors, which is in sample 3, this last one right here.
So what's the number at the beginning?
That 4 represents how many statements you have.
So that's like 4 guesses.
Yeah, sure. You can think of it as guess as well. Yeah. So now what's our goal? Cool. So now what's our goal? So we have all these statements, but now our goal is to try to find the minimum amount of toppings needed to satisfy our guess. So for example, I guess we can look back to sample 1. We have peppers, so we for sure know that we're going to be having peppers. That makes our count 1. We for sure know that we're going to have spinach, and we for sure know that we're going to have feta. That means that we are 100% positive that we would have at least 3 toppings so far. Now, if we look at the implicative statement, can we get tomatoes? Well, let's ask ourselves, do we have spinach and olives? We do have spinach, but we don't have olives. Therefore, we cannot obtain tomatoes, or we cannot add tomatoes to our list of toppings we should add to a pizza. Which is why the output is 3. If, you know what, let's do sample 2. Sample 2 is a little bit different. We could satisfy one of these implicative statements. We for sure know we're going to have pepperoni and pineapple, and in addition, also ham. So that's 3 toppings that we do want to add. Can we satisfy any other statements? We actually could, because if you see this last implicative statement, it says if we have pineapple and ham, which we do, because we have pineapple right there, then ham right here, then let's add bacon. So that's why our answer is 4, because the first 3 were absolute, and then this last one gave us bacon, and that made our topping 4. We cannot get mushrooms because although, oh, actually no, we don't have, oh no, yeah, we do. Although we have pepperoni, we don't have sausage. Yeah.
So the ones that are just the toppings of like pepperoni, pineapple, those lines that just contain the topping, they need to be added.
Yeah, 100%. Yeah. Yes.
Because they're already added in the if statement, since they're already there, then you need to get a bacon.
Exactly. So those absolute statements, 100% we are going to have them or add them. And then we might want to check the other implicative statements and see if we can satisfy that constraint and add an extra topping. So now I want to ask you guys, what if this first implicative statement, what if it said if pepperoni and bacon, then sausage? What would our output look like? 5, okay. Does anyone agree or disagree? Okay, Dembo agrees. Okay, that's a head nod. Okay, we have 3. Any more head nods? No, okay, that's 1 no. Okay, David's not paying attention. All right, so let's think about it. We for sure know we have pepperoni, pineapple, and ham. Therefore, we can satisfy this last constraint. And now we can add bacon. But now that we just added bacon, we can go back to the first constraint and check if pepperoni and bacon, we do have both of those because we recently just added bacon. Therefore, we could get mushroom.
It's not we could, we have to get mushroom.
Yeah, you're right. We have to get mushrooms. All right, does that part make sense? Yeah, all right, cool. Now, what if instead of pepperoni and sausage, it would be pepperoni or sausage? It stays at 4? It goes to 5, yeah.
Oh wait, it's pepperoni or the sausage.
Yeah.
You're not moving it to bacon?
No, I'm talking about this one. If we change that and to an or, then it still satisfies the constraint because we only need to match one of them. We need to have either pepperoni or sausage. So that's where the 5 comes from. Okay, so are we all solid in our understanding of this problem? Yeah? Yes? Okay, cool. So let me turn the system off. Let's go to the board now. Okay. All right, cool. Let me just move the camera. All right. So now we want to talk about how we can represent this problem with a data structure or some sort of way where we can program it to make it a little bit easier for us to solve. Let me first write down, we had peppers. I think it was pepperoni. You know, I don't know how to spell pepperoni, so I'm just going to write peppers. Just, yeah, it is, but it's fine. I can just change the statement. All right, so I changed it just a little bit. Does anyone want to give me the answer to this, if this was your input? 4, all right, you guys agree? Yeah. Okay, David agrees. Dembo, do you agree? Yeah. Okay, we have a consensus, good. Wait, you guys agree as well? Yes? You understand where the 4 comes from? Yeah, okay, cool. All right, yeah, just to make sure, our absolute statements are peppers, pineapple, and ham. Then our implicative is this last one, which is if ham and peppers, then bacon. We have ham, and we also have peppers. Therefore, we can get bacon. Now we have 1, 2, 3, and then 4, which is why the answer is 4. Another way to represent this is actually through a graph. Let's say peppers was one node. Pineapple was another. And then ham, still last one. To get bacon, we must have both ham and peppers. So you can think of this kind of as two edges, going from ham and peppers to bacon. There we go. And then peppers and sausage, that's the only way we can get mushrooms. Let's write sausage down here. There we go. Now we want to first start off with which ones are absolute and were given to us, and we have no decision on whether or not we can take yes or no. In that case, those nodes are going to be peppers, pineapple, and then ham. We start off with those so we can start doing this search at those nodes. Once we visit one of these nodes, we can think of it as a queue. Let's say I first visit pineapple. I want to see its adjacent nodes. What does pineapple go to? In this case, it doesn't go to anything, so you must leave it as is. But now let's try ham. Since we have ham, we know we can satisfy one constraint, which in this case is bacon. Therefore, since we can satisfy bacon, let's remove its edge to bacon. It makes sense why I'm removing edge and why we must remove an edge pretty soon. The next one we want to try, we finally tried our both pineapples, we tried our ham. Now we just need peppers. So at peppers, let's see its adjacent nodes. What nodes can I go to from peppers? And that's, in this case, it's mushrooms and bacon. So I just finished with peppers. Now, where do we go to next? Which ones do we want to search at? It's the ones that have a 0 in degree of edges. In this case, bacon has 0 in degrees. So you can think of this as kind of topological sorting, where the nodes you do want to discover first are the ones with 0 in degrees. So since bacon has 0 in degrees, that means we have satisfied the statement that gave us bacon, which is this second statement right here. This is the first. So now since we satisfied that, let's explore it and let's see what adjacent nodes or what statements bacon is a part of and we can satisfy. In this case, since it has no out degrees, it's 0. So once we finish with that, we have explored bacon. And now, which one is the next one we want to explore? Sausage. Yes, but since we were never given sausage, we can't actually start at sausage. And we were never told to go to sausage. Yeah.
Wait, can you draw the same graph?
Yeah.
But instead of sausage, put bacon.
Yeah, I
And
was
see
gonna
how
say
that
that.
works.
What, instead of sausage here?
Yeah, the same thing you had, just change the sausage to bacon.
This one is going to nothing.
Basically, remove sausage and add mashed bacon and mushroom.
Yeah, okay, I see what you guys are getting at. But if I'm adding, change that to bacon, it must be here now. All right, so this is a good problem, right? So now we're also changing the statement. So that's if peppers and instead of sausage, bacon. We know we can satisfy this statement, correct? Because we do have peppers, we actually start off with it. And then later on, we eventually pick up bacon. So we must get mushrooms. So let's do the exact same thing. Pineapple doesn't have any out degrees. It doesn't have any adjacent nodes, so we don't really change anything. For ham, we do have some adjacent nodes. In this case, it's bacon. So let's remove that out degree edge. Then once we look at peppers, let's do the exact same thing. Now we arrive at bacon because it has 0 in degrees. Bacon wasn't given to us in an absolute statement, but we arrived at it by solving an implicative statement, by removing those edges. So since its in degree is now 0, we could add it to our topping list. So now since we're here, let's look at its children, or its adjacent nodes. Children is more of a tree thing. But let's look at its adjacent nodes. In this case, it's mushrooms. And let's remove it. And now let's ask ourselves, since we just removed this edge, let's look at the node that edge was going to. And if its in degree is 0, let's add it to our list. Because it's telling us that we satisfied it. In this case, its in degree is 0. So we will explore it. It then doesn't have any out degrees, so we're done. And that's how we get 5.
Got a question. When you wrote the same graph but with sausage previously, that sausage graph, the sausage node had an in degree of 0. So why didn't we explore that?
Because we didn't start off with it, but we started off in our queue,
But we didn't start off with bacon either.
but we arrived at it.
Or we're arriving at the sausage.
We never arrive at sausage. There's no statement here that makes us arrive at sausage.
But with the if statement, it's if peppers and sausage.
Yeah, those are the requirements. The ones we arrive at is after the end.
So that's how we traverse the tree with the things after that.
We traverse the tree by starting off with our absolute first, and then by marking off those absolutes. If it satisfies a implicative statement, then we want to look at whatever that implicative statement gives us. In this case, it was bacon.
It's like a depth first search.
It's more of a, not really depth first search. You can think of it more as BFS because it's topological sorting, so you will be using a queue. Like in your queue, first you would have 1, 2, and then 3, right? So that will be, your queue will consist of these 3. And then you iterate over this queue, taking off the in degrees, taking off the edges that go to other nodes. And then if that other node now has an in degree of 0, then you want to add it to your queue. So
Possible implementing it with DFS.
a topological sorting? Yeah, you can do DFS as well. I think it's better BFS. Because DFS, you might go to ham, and then you can stop at bacon, but then you have to, I think you still need a queue.
No, BFS.
I don't know, unless you start off over.
Peppers, pineapple, ham. Then you do from ham. You have peppers and bacon. And
Yeah, if you start your DFS with your absolute nodes, with your absolute peppers.
You just do it in DFS, but before you return, you add it into a stack, which keeps it in reverse order. Because when you do DFS, like the node you're gonna start from, you just have to make sure that the rows you start from is the one without any in-betweens, right? So
Yeah, okay.
Like the deeper you go in your DFS score, like if you go deeper in your DFS score, that means that there was like a previous constraint that you just jumped, right?
Yeah,
That you just removed.
that you only had one, and then you just remove it at DFS call.
When you go to the last one before you return, that's when you add it to a stack, and that keeps it in a reverse order, because the stack keeps it in reverse order, and then the order in which you get the stack at the end of your DFS call, that will give you a topological order. Like I don't know if that implementation is gonna solve this problem exactly, but that would also give you a DFS call, as in you already construct the graph.
Okay, then yeah. All right, then yeah, you can do it. I didn't know you can do topological sorting with DFS though. But yeah.
Show you after class.
All right, yeah, do. Or send it to me through Discord. All right, so that's that statement, but we did that statement only for ands. How will we do it for ors? If anyone want to give it a try. I'll reconstruct the graph. Can't find it. Wow, I actually lost it. Oh yeah, go for it.
But if you like map the node itself as an OR node, right? Like let's say like you have multiple tokens that like you need to satisfy different ORs to get to that. And if you map that node like as an OR, so like if just one edge gets to it, you can immediately eliminate all the other edges without them having to lead to that edge.
Yeah. So if you're doing it as a graph like this, let's say for mushrooms, instead of and, let's say it was or. You can have a designated or node. That says mushroom. So you have a designated OR node, or if you know that this is an OR node, and you're about to delete this edge, you first check if this node is an OR node. If it's an OR node, then you know you can instantly go to your mushrooms. So that's one way of doing it. So if you either delete this edge or this edge, you would instantly arrive at mushrooms. So look at your neighboring node. First check what type of node is that. Is that node a topping, or is it a statement type? Or a logical operator, whatever you want to call it. If it's an OR, if the statement type is an OR, then you know you can instantly go to the next one, and so go ahead and do that. Another way of doing it, we're going to be implementing this with a hash map. Instead of actually creating nodes and adding the edges, it's still the same thing, it's still a graph. But if you were doing this in a hash map, you just have to set the requirements to just one. If that statement itself, if you keep a track of which statements are ORs and which ones are ANDs, if you meet a requirement for one of the OR statements, then go ahead and add whatever that statement would have given you. Yeah.
What if you do those statements, like you have to go back to the statements?
Yeah, so you're going to be doing this, go back to the statements?
Like for you to get the first statement, like let's say instead of or it was an and, the peppers are bacon. For you to get the first statement, then you need to go to the second one first. So how would you like start that? Like, because you need to get to the second one.
So you're going to be adding, first you're going to be starting off with the absolute, right?
Yeah.
And then so this is going to be in your queue, these three are going to be in your queue, and then you want to iterate over all of your statements. And see from all of your statements, if the current one you're looking at, for example, let's say the first one I popped from my queue is peppers, you want to look at all the statements. Yeah, all the statements in general. So let's say I have 5 statements, I'm still going to look at all 5. If the first statement has peppers, go ahead and remove it. If the second one has peppers, go ahead and remove it. Then your next one you pop from your queue is going to be pineapples. In this case, I also just added mushrooms to my queue because I already satisfied one of the ORs. So let's keep that in mind. Now pineapples, it's in none of the statements. Now ham, it's in this statement.
Wait, you're saying that you added bacon and mushroom to your queue?
No, I added only mushroom
Why?
because I don't have bacon yet.
Can you put and instead of or really quick?
Yeah.
Okay, so then it's peppers, and then you cross out the peppers, and then you do pineapples, right?
Yeah, and then I do pineapple, and then I do ham. Ham is here, peppers is here. Since I just crossed out a ham, I know I already meet all the requirements for this statement, so I'm going to add bacon to my queue. The next one I process is going to be bacon. I look over here, cross it out, I add mushrooms to my queue.
Yeah.
So the main thing about this problem is having it set up correctly, having your hash maps to know which statements requires what, and if that statement is satisfied, what would it give you? So that's the main thing, which makes it a little bit messy.
What happens if 2 statements arrive at the same ingredient?
Yeah, so I'm glad you said that, yeah. So we're going to be using a set as well.
Okay.
So if we already seen this ingredient, let's not go ahead and process it again. Because we have already crossed it out from all the statements it was referenced before. So there's no need to do that repeated work.
Okay.
Yeah.
I just have one question. If you were to do this, right, implement this topological sort algorithm, how do you differentiate between like, remember when we had the sausage but we didn't arrive at it?
When we had the what?
When we had the
Yeah,
sausage
yeah.
but we didn't arrive at it, so we couldn't use it, right? But if you're implementing like a topological sort thing, it still has 0 in degrees. So how do you make that difference?
It depends. In this case, it depends where your queue starts off with. We don't want to add to our queue all the nodes that have 0 in degrees. What we want to add to our queues are these absolute statements.
Oh, I see what
Yeah.
you're saying. Again, because it doesn't arrive at anything, you
Yeah.
never get to it.
So that's why I said topological sorting. But number one, you don't use the order, and you don't do every node that has 0 in degree. And that even goes for absolute statements. Because you can have a graph where you start off with, let's say, A, correct? And then if you have A, so this is just an extremely simple statement. If A, then B. This is as simple as I can get. And this is possible. If you have A, then we're going to get B. And then if B, then A. So notice this doesn't have 0 in degree, but since it's an absolute, we still do want to start there. So there's little places where it does differentiate from just regular topological sorting. So in this case, like you said, A is given to us twice, but since we're using a set, we only count it once. So yeah, I'm glad you asked that. So now do we have a rough idea of how this problem is mapped out?
What if you're not given A?
Huh?
Then it's an invalid statement.
Yeah, if we're just not given anything at all, we're not given any absolute, then we know for sure we cannot satisfy any implicative statement.
How would you identify it?
Okay, good. Yeah, that's actually something else I need to mention. Before we do all this work, we first need to parse the input. For example, for this input right here, we can consider this as an OR statement. So we have to tell ourselves that for this, let's call this statement number 1, this statement number 2. Let's say the statement number 1, it requires A. That's it. Let's just call this one hash map. Statement number 2 requires B. And that's the end of our hash map or dictionary. Now let's say if we achieve statement 1, then we will be given topping B. And if we achieve statement 2, then we'll be given topping A. So this is something we want to keep track. These are 2 hash maps that when I get into the code, you see I do have to implement. And then something else is those statements that are ORs. OR statements we need to keep track of. So once we do delete an edge or remove a requirement from that statement, we know we can instantly receive its whatever it equals. So we can have, this time instead of a hash map, a set. In Python, it's actually the same notation. Actually, no, I just write it this. So here we want to include all the statements that are ORs. In this case, 1 and 2 are OR statements. And as I will show you guys right now, this is all you need to solve the problem. 2 hash maps and a set. And of course, your queue. I think one of them is actually queue. Huh?
How are those 2 statements OR?
You can take it as ORs or as ANDs. The way I did it, I understood it as ORs. So you can think of it as A or nothing else, then B.
Oh, okay.
Yeah. You also think of it as if A and anything else, then B. All right, so you guys want to get into the code now? Yeah? All right. Bear with me. Okay. Okay. Finally. Okay. All right, cool.
I have one more question.
Yeah.
Are we assuming there are not going to be cycles like here statement 1 and 2?
Yeah. So as you can see in problem one, not in problem, in this example I did, there is a cycle, but since we have already visited A, we won't do any of its repeated work, and that edge would just cancel out.
Okay.
Yeah.
But if there is a cycle, at least one node has to be absolute.
Yeah. Either one node needs to be given, either through an absolute or we achieved it through one of the implicative statements. All right, cool. So now we can start getting into the code. I have 22 minutes, so hopefully this doesn't take too long. So the first thing we want to declare in this file is two things. Number one, the invalid topping names. Because as I said, we want to parse these inputs. And we want to, from the implicative statements, we want to get the toppings that are required and what type of statement type it is. So whether it's an or and an and whatever topping that gives us if we satisfy its constraints. So I'm just going to start off by doing a set of strings. And I type really slow, so please bear with me. Invalid topping. I'm going to set this equal to if and or and then. The problem statement itself tells us that a topping would never have this name. So if we currently strip the input by spaces and we see that the current word we've we're looking at is inside of this set, then we know it's not a topping and we can ignore it, throw it to the side. But we also care about the type a statement is. We care about if it's an or and an and. So we need to do another set of strings. Let's call it statement types. We'll call this or and and. So if it's an or and an and, it's going to be inside of this set. And we want to determine that because we want to know what type this implicative statement currently is. Now we can get into the function that does most of our input parsing. It's going to return a vector of strings. And I'm going to call it get topping from statement. As an input, it just takes the statement, just like that. Now let's declare that vector that we're going to be returning. Let's call it vector of strings, and let's call it toppings. Okay, and now we're going to be building out a word. We're going to be splitting it by the spaces, and we want to get everything between spaces. So let's call topping string. It's going to represent whatever word we're currently looking at. Then let's just get the size of that statement string. Let's make this equal. So now we can get into the real logic of parsing this input. So we first going to want to input a for loop. So that's an n I plus plus. So topping, let's set these equal to empty in case we have previously built something out. And now to actually get these, or to build this word, we're going to want a while loop. So while n, where I is less than n, and the character in the inside of the statement string at index I does not equal a space. So what this while loop is going to do is going to get every single word between the spaces. And that's it. Let's actually do topping plus equal statement at index I. And let's increment I if this was successful. So far that's the logic just for getting every single word between spaces. Now we want to do something with this. So if invalid topping names dot find topping does not equal invalid topping names dot end. This is basically telling us that if the current word we have just built out, if it's not if, and, or then we know it's a topping name. Therefore, we want to add it to our array of toppings. Now we're going to want another else if. Now we're going to want this to get the statement type. I need to make sure to be writing all this correctly. There we go. Right. So now if this topping, if this current word that you just built out, it's either or and, then we know that tells us what type of statement this currently is, what type of implicative statement it is. And we're going to want to save this because we want to, later on, once we're parsing the strings, we want to determine whether the statement is an and, because that's important to know if we need to remove all the edges going to that node. But if it's an or, we just need to remove one of those edges. So we need to have information on what type of statement it is. Is equal to topping. Right, that's enough for this screenshot. Right. And now we can finish with that for loop. Let that do whatever work it does. It builds out the words, and it adds it to the toppings and the statement type. Now, if the statement type does not equal an empty string, then we know that this was not an absolute statement. Does anyone want to tell me why? Test your guys' code literacy, I guess. Yeah. Okay, so that for loop and the while loop, it's going to be getting all the words between spaces. For example, if I were to run this with this statement number 1, I'll be getting if A, then B. So that's what topping will be. In the first run, topping will be if. Then in the next iteration, topping will be A. The third iteration will be then. The fourth will be B. Then in this if right here, it says if this topping or this word that we currently built out, if it's not inside of this set, then we know it's a topping name. Therefore, let's add it to our topping array. Else if it is inside of here, then let's also check if it's inside of this or and set. We want to know that because we want to know what type of statement this is. And if that's the case, then let's save it inside of our statement type string. So the answer to the question, unless you guys want to respond, anyone? Yeah. So the statement type, yeah, go ahead. All right. Cool. All right. If the statement type does not equal empty, then we know this was an implicative statement. If it was empty, then we know it was an absolute statement. Why does that matter? If it's an implicative, then we do have to save the statement type. If it's absolute, we don't have to save the statement type, because there will be no ors and there will be no ands. So how do we save it? Well, we simply just add it to our toppings array. Push back, statement type. Now else if statement type equals empty and toppings dot size. I'll explain this right now. Give me a second. All right. Anyone want to explain this to me? This is one of the cases that we have to work around. So how can our topping size be equal to 2, right? So that means there are at least 2 toppings in the statement. Therefore, we already know it's implicative, right? So we know it's not absolute. If it was absolute, topping size will be equal to 1. So how can our topping size be equal to 2 and statement type still be empty? Exactly. We have one of these cases right here. Notice how there's no ors and ands, but it's still an implicative. And here, if it's this type of statement, it's always going to have two toppings inside our topping array. So if that's the case, they want to force the statement type to be or. That's just how I do it. You can probably do it and as well. But I think or is a little bit easier. But you guys can try it out. This is all we really need for this string parsing or input parsing. Then we can just return toppings. Let me save to see if I made any errors anywhere. I did. Okay, I think that's one error gone. All right, toppings, sorry. And then toppings here as well. All right, cool. So that's just for parsing the input. That's a good amount of lines just for parsing. I think Python's super easy, just split by spaces. But we don't have that luxury here in C++. All right, so now let's get into the actual logic for solving this code. And I should have done this a while ago, but there we go. You guys can probably see that better. The first thing is we want to take into in the amount of constraints we have. So that's that first number that we saw. It tells us how many of these statements we see or how many guests gave their recommendations or their requirements or whatever. We also, just to get rid of a bug, we need to get the char, because I'll explain later in a while. Then we have to create our queue. I'm going to call this queue singletons, because this is just, this starts off with just a single or absolute statements. It's just a name Gary gave in his lecture, so I'm just going to go ahead and stick with it. So those singletons is initially going to consist of just the absolute statements, but now we also want to take care of the implicative statements. And we can do that, by creating a vector of strings. So an array of strings. Why do we want to do that? Because we want a vector of this right here is going to be a vector itself that consists of A, B, or. This one, B, A, or. And we want to add all those statements within one vector. This inner right here is coming from what we're going to return. All right, so now let's iterate over our constraints. And let's actually get all of them. Let's call this constraint. And then let's get that line right there. Right, and the reason, like I said, I will eventually explain it. The reason we're calling getChar is because if we try to call getLine, then there'll be an empty string, and it wouldn't really get the first line of our input. So to fix that bug, we need to call getChar. Now let's create a vector of strings. Let's call this O toppings in statement. No, it's pretty long, but we're trying to have some nice clean code right here. And this is going to be equal to whatever this input parsing function gives us. And let's pass it that constraint right there. Yeah. What's wrong, man? You're not following ahead perfectly? All right, so we just got all of the toppings within the current constraint. And keep in mind they can either be absolute or implicative, so we need to do some logic for both of them. If all topping in statement dot size equals, anyone want to tell me? I'm doing for absolute. If it's absolute, what would the size be? 1, yeah. So if it's 1, then let's call it this. Then we just have one single singleton. And we can achieve that by calling the back, so getting the top, or getting the last one within this vector. And since it's only 1, it gets the first one, the first and the last. But let's also use pop it by calling pop back. Pretty unfortunate how there has to be 2 function calls. I know in Python it's only .pop, but whatever. It gets the last one in this array. So it's like pop in Python, but in Python it both removes it and gives it to you. But here in C++, pop back doesn't return anything.
Oh, okay.
Yeah.
You call back and then you call pop.
Exactly. So we just got this current topping. There's only one topping. We currently got whatever topping it is or whatever name it is. And since this is an absolute, this is for absolute statements, we need to add it to our queue. So singletons dot push singleton. Else, if the size is greater than 1, then we know it was an implicative. So let's add it to our statements vector that we define right up here. And then let's push back all toppings in statement. Right, and that's enough for that one. Give me 1 second. Make sure I find the next. All right, cool. So essentially, right up to this line, we would have done 2 things. All the absolute statements would have been added to our queue, which is correct because those are the ones we'll be starting off with first. The second thing is inside of our statements vector, that's going to contain all the implicative statements. So far, everything is organized neatly in absolute and implicative. Now we need to do some logic with this. I'm first going to define a statement count and set that equal to 0, which this is, it's eventually going to represent how many statements, implicative statements there are. And now I'm going to initialize these hash maps and sets that I told you guys. It's extremely important to have those 3. So the first one is going to be a set of integers. And let's call this OR statements. this OR statements, if the statement count is in here, then that's telling us, hey, this statement is an OR. I don't have an example right here. Or 1 and 2 is an OR. So that's why it's added to this set right here. That would tell us that we only need one of these to get whatever result the statement gives us. But as I just said, we need to know what are the requirements for this statement and what is the result of this statement if we satisfy it. And that's where the other two hash maps come into play. So we can create an unordered map. And it's going to be int and then string. And integer is the key because that is the statement count. And then the value is a string because this is what it's going to equal. If this statement is satisfied, then it's going to give us a topping which is of type string. So let's call this statement equals. Then I'm going to do something pretty similar. But instead of here, it's going to be an unordered set of strings. And then we're going to call this statement requires. So why did I do an unordered set? Because just in case there's a implicative statement that says if A, or A, or A, or A, then B. We don't want all those ORs multiple times. We only want it to be shown once. Hello?
Hi. Is there a class going on here?
Yeah, it's a lecture. I think we have it booked to 5.
Is that your event?
It's at 5 p.m. Yeah.
Oh. Sorry for interrupting.
No, it's fine. All right. So don't worry, we're getting pretty close to finishing up. No pressure. So now we need to iterate over all these implicative statements which we saved inside our statements array. And we need to set them in these hash maps and set correctly. So let's go ahead and do that. For vector of string, call this statement inside of all our statements. Perfect. And then the statement type, as you remember, we added it all the way at the back. When we were parsing the input, if the statement type is not empty, then it's the last thing we pushed to our vector. So we can simply get the statement type just by pushing or getting the back. Now that we received it, let's also pop it. Perfect. And then now, since we just popped the statement type, the next last thing is going to be whatever the statement will give us if we satisfy it. So we can get that by just looking at the back again. And then let's pop it. Bam. So this works out because how we set up our get toppings from statement function. So we know what it equals and what type of statement type it is. Now let's create an unordered map, an unordered set of type string, and we're going to call this requires. So the remaining strings inside of the statement vector is going to be everything that statement requires for it to be satisfied. And we want to add it to this unordered set because of how I just said it could be if A or A or A. So now let's iterate for string inside of statement. Let's add it to this set. Let's insert, correct? Yes. Statement requires. There we go. So now we have set everything up. We know what the statement equals. We know what type of statement it is. And we know all the requirements that that statement needs to be satisfied. So we can add it to our hash maps right now. So let's add it to the statement equals hash map first, where the key is the statement count. And the value is statement equals. Now we're going to do something pretty similar, but instead of for statement equals, it's going to be for statement requires, and we're going to make that equal to requires. Let me save to see if I have any errors anywhere. Oh. Let's change that to equals. Cool. All right. So now if statement type is equal to an OR, then we want to add it to this set of all the OR statements. And we can just add it by using its statement count. And then finally, the last thing we want to do is increment statement count in case there's another. Right, now we're on to the last thing. So far, everything we built here, we have separated the statements, what the statement requires, and what it will give us if it's satisfied. And we also know which statements are an OR type. So let's create our answer variable. Let's set that equal to 0. And then let's set this set of strings, call this scene singletons. So like you pointed out, if there's a cycle, we know not to do that work again because we have already added it previously to this set. All right, last line of code, or last couple of lines. So while our queue, where our queue is initially all the absolute statements, so while that is not empty, we want to do some work. First, let's get the current singleton, or the current topping. We can get it by looking at the front of the queue. And then let's pop the front. So we got the current one in our queue. And now if scene singletons.find cur singleton. If we've seen this singleton before, then let's not do whatever work we're about to add. And we can do that by just continuing to the next iteration of this while loop. Else, we have never seen this topping before, so let's insert it to our scene set, and let's increment our count. Finally, all right, now this is actually the last piece of logic. It's the for loop, where we're iterating over every single statement and see if we can satisfy some portion of that statement with the current topping we're on. So for int I is equal to 0, or I is less than statement count, I++. Let's create an unordered set of strings. The reason we're creating this is because this is actually be a pointer to the requirements for this statement. Statement requires and I. So let's go over all the statements for this current statement. Let's see what it requires. And if cur requirements dot find cur singleton does not equal cur requirements dot find dot end. So if we look through this unordered set and we find that this current topping we're on, called cur singleton, is inside that set, then we know we can satisfy some portion of it. And we can do that by doing cur requirements erase cur singleton. Now, since we just removed this requirement from that statement, there's something else we need to check. We now need to check if that statement requires nothing, if we have satisfied it completely. We can simply do that by doing, we can do it by looking at all the OR statements. So if this current statement that we're looking at, if we just removed one of the requirements, and it's also an OR statement, then we can instantly get whatever that statement gives us. We could first set cur requirements to be empty. And then here, outside of this for loop, outside of that if block, if cur requirements dot size is equal to empty, then we know we satisfied all of its constraints, and we can push whatever that statement equals. Statement equals there. And that's all of our logic for that while loop, which is kind of doing of that topological sorting that we talked about. Then finally, we can just return answer. And if let's save to see if I don't have any errors. All right, I have a couple of errors. It's because this is a pointer, therefore I need to use that. This is singletons. All right, I don't see any errors other than here because I removed a whole bunch of code. Let's make this long. All right, cool. So this is all the code we really need. I know you guys completely got it on the first try and fully understood it, so there's no need to talk about it again. But now we can actually test it by creating a new file. Call it input.txt. If this doesn't work, it'll be really embarrassing. But I don't expect it to work, to be honest, because that was first try. So let's try to run the code. Let's see if we made any errors. We definitely did. Oh, it's right here. Oh, it's equals. Okay, so let's run it one more time. And we have segmentation fault, which is one of the worst errors you can get. And might take a while to fix. Same constraints 4. Okay. Let's see how fast I can debug this. If not, you guys will just have to trust. Oh, wait, actually. We can go to right here. So this code does work. Let's actually use that input. It's the same code. I took it from the same screenshots. But I guess while I was rewriting it, I made some error that didn't catch. So let's write that input. Then let's run this code. As you can see, it looks exactly the same because it is. And if we were to run it and look at our output, we see that our output is 3. And that does match the output for that file. So I guess now the big reveal, I can submit it to the mock competition. Let's go over here. Let's submit. Remove all of this junk. All right. Let's see. Should get accepted. It's the same code I used for last time. Hello.
How long you gonna have this one?
Uh,
Yeah, leave us come, we have a workshop here. Leave us 5 minutes ahead because we gotta set up the.
yeah. Well, I'm about to finish right now. In like in 2 minutes, I'll start packing.
Thank you.
Yeah. And it gets accepted. Cool. So as you can see, that code does work. All right. Huh?
Did you debug it?
No, I just used the same code I took screenshots from. I guess while I was copying over, I made some bug that I didn't catch. But it's the exact same code. As you can see, I'm still using that to go through the input and parse it, still using the same sets. I can show you the 2 hash maps in the 1 set. Everything is still exactly the same. So yeah, other than that, thank you guys for attending. I'm kind of getting rushed. But yeah, that's it.